So we had to face some facts with the Ising model. When we did the trace out, when we forced this particular projection operator in the language of the cellular automata, when we fixed this particular coarse graining, what we got back was a model that felt intractable. And in particular, it went from being a model that was pairwise to being a model that was not only pairwise, it had these long-range interactions, and not only that, but it even had these synergistic ones. And then I said, okay, look, let's just do our best, and we're going to neglect all of the interactions that are not the blue ones, and because we're dropping a bunch of them, we're going to augment those blue interactions by the long-range green interactions. And so what that means in the end is we're saying that when you coarse grain the lattice for the Ising model, the theory renormalizes in the following fashion. It stays pairwise, but now the coupling term beta goes to 3/8 log cosh for beta. So, just as we did in the Markov chain case, let's ask how this model flows as we continue to do coarse graining transformations. If you remember in the Markov chain case, I began with a model defined by 2 parameters, and as I evolved it through time, or rather as I coarse grained the data and asked which model best fit the data, as I did that, all of those Markov chains converged into a single 1-parameter lower dimensional family. And once you got to that lower dimensional family, you stuck there and you didn't move. So in that case, the Markov chains all coarse grained, they all renormalized to a single, or rather to a set of points, a line of points, and each Markov chain picked a particular point to land on top of. Here in this case, we have a model in the end defined only by 1 parameter beta. We keep the lattice structure fixed, so the only thing that matters is what beta is. And so in fact, now we have a 1-parameter model. And what I'm going to say is, okay, let's do one coarse graining step. I take beta to 3/8 log cosh beta. So that function log cosh for beta, that function looks something like this as beta gets large. So an easy way to see what this transformation means is to draw the line corresponding to beta equals beta. And it goes something like this. So what's happening here? What happens when we continue to coarse grain the Ising model using the decimation transformation for a particular value of beta? So let's say we begin here. If we begin here and we take 3/8 log cosh for beta, we end up here. Let's say we then feed this value back into this formula here. In other words, we're going to decimate a second time. So that takes us here, and then we find ourselves there when we do the second decimation transformation. And again, if we start here and do a decimation transformation, here's the value of beta that corresponds to, and that gets mapped all the way down to here. And in fact, wherever you begin, you end up bouncing upon repeated transformations all the way down to beta equals 0. So when beta is small, when the coupling between 2 nodes is small, when you do this decimation transformation, it makes the couplings even weaker. So the system gets driven towards this decoupled state. And effectively, what that means is if you zoom out enough from the Ising model and you look at the patterns, it looks like television snow. Each node is totally uncorrelated with the node next to it. There's no long-range correlations that are visible in the data. Okay, let's take a very large value of beta. For a physicist, that corresponds to a low temperature. Beta is the inverse temperature. For the rest of us, we can just think of a large beta, meaning that nodes really like to be in the same state. You're much more likely to find patches where all the nodes agree on the value. And in that case, when beta is large, then when we do the renormalization group transformation, beta goes to 3/8 log cosh for beta. What we find is, in fact, that it's larger than the original beta. We're above the green line. And when we do that again, when we do the transformation a second time, it gets even larger, and it gets even larger. And in fact, in this case, beta gets larger and larger every time you do the transformation. So when beta is small, it gets smaller. When beta is large, it gets larger. This is like sort of in the Bible, right? The Matthew effect. Those beta who have, more will be given to them. Those who have little, what little they have will be taken away. And so in fact, you find two fixed points in this system, or at least two fixed points that we've seen so far. In one case, beta gets driven to 0, and in fact, when beta equals 0, you can see that this here feeds into 0, goes to 3/8 log cosh 0 is 0, or sorry, cosh 0 is 1, log cosh 0 is 0. So that's a fixed point. There's another one where beta gets driven to infinity, but somewhere in the middle is this magical point. This is like rule 150 for the cellular automata, right? This is like the stationary Markov chain. This is a point where the system becomes self-similar. When I do this decimation transformation, I'll turn it around like this and get the blue lines, and then I do the same thing, and I cross that guy out, and that guy out, do the same thing, and turn it again. When I keep doing that, I actually keep getting back the same value of beta. When I zoom out, the system seems no more or less coupled than it did to begin with. So this is a magical point in the system. This one here is somewhat trivial. The system decouples. This point here, when beta goes to infinity, means the system is so strongly coupled that when you zoom out enough, basically everything's all in the same state. It's all either +1 or -1. When you're at this critical fixed point of the renormalization group transformation, when you're at that critical fixed point, in fact, there, when you zoom out, the system has the same dynamics as it did before. Now, one objection to this whole analysis is like, hey, wait a second, right? We know that this is only an approximate way to do the transformation. This is only an approximate way to actually scale the system up, given that RG choice, given that coarse-graining choice. You know, we had to do this approximation. We said, oh, you know, I guess kind of add the blue lines and the green lines, just make them all blue lines and neglect this one here. So it is remarkably possible to come up with a transformation for this model that you can solve exactly. It's much more complicated. It was solved by somebody called Onsager in the 1940s. But this one is good enough. And in fact, one way you know this one is good enough is it finds that this crossover point is approximately equal to like 0.50 something, 0.8. Okay? That's what our sort of approximate solution to the Ising model decimation coarse-graining gave us. In fact, the true value is 0.44069, and there's like lots of things after that. This is the exact one. So we know, look, we didn't do too bad, right? What we did was we came up not with an exact sort of commuting diagram transformation. We came up with one that like was just about okay. And by the way, you can do another thing, which is you can say, look, that's the value of beta where it stays fixed. One of the terms I know I neglected, that was S4. S4 was equal to 1/2 log cosh 2 beta. This is a nice trick somebody pointed out to me once, is that if you feed in the 0.5 into that one there, you get that that S4 is like 0.05 or something like that. It's actually down by a factor of 10. So that coupling there is a lot smaller, and perhaps you feel a little better about neglecting it. It's only 10% of the original coupling. So that's another way to justify what we're doing. So what have we done here? This is sort of the final step in your renormalization education. Because in this case here, we came up with a coarse-graining that we liked, but we were forced to make it only approximate because it took us out of the model class by inducing, let's say, these synergistic terms here. It took us out of the model class, but we sort of were bold enough to say, okay, let's just force it back into the model class by taking this lattice and kind of pushing things around to get them close enough. And when we did that approximate solution, we actually found that things worked pretty well. It matched the exact solution, and then you say, okay, fine, well, why don't I just do the exact solution? Well, one answer is it just takes a lot longer. Another answer is you may not have an exact solution because you may have only, for example, a set of simulations. And that brings us to the final point of this Ising model renormalization module, this part where we found this fixed point, because what we're going to ask now is what on earth does this fixed point mean in the real world? What is actually happening when the system, when the beta is fixed so precisely that it happens to lie here? Notice that if it's just fraction low or a fraction high, it will be carried off to either infinity, massively correlated, or 0, totally uncorrelated. But if it sits there, it has this amazing scale invariant property. And we'll see what that is in the next section.